I will talk about more about transitioning from the lab scale to the pilot scale and eventually demonstration scale, and in regards to fermentation and downstream processing. So there is a long process development change from laboratory through pilot scale, demonstration scale, and to the commercial scale. And there are a lot of bottlenecks on the way, and a lot of them can be avoided if you think about industrialization early. Your steps need to be scalable. You have to pay attention to availability of chemicals, waste, and waste disposal, and the costs of each step. And I will go a bit more in detail, and I will finish up with an example from our experience. So in upstream processing, there's little value in optimizing shake flask cultures, as in industry, you need to switch to bioreactors anyway. So you can also do it early, as the previous presenter has already showed. And also, one of our experiences is you need to take a look at regulatory measures. There are only a few contract manufacturers that can actually handle biosafety level 2. So you should rather work with biosafety level 1. And keep in mind that even in different countries, different strains are regarded as biosafety level 1. For example, we were working with Aspergillus terreus, which is considered biosafety level 2 in Germany and 1 in the Netherlands. So we had a problem in this project. Coming back to the fermenter versus shake flask issue. Fermenters offer a much tighter control of pH or dissolved oxygen concentration. And it also allows feeding. But on the downside, stirred systems can cause much higher shear stress. And that's something you have to work out before going into pilot or demonstration scale. Also, you need to think about cleaning. We had effects of anti-foam that it attached itself to the mantle or to the inner part of the fermenter, and you cannot dismantle a big bioreactor easily to clean by hand. Everything needs to be cleaned in place by flushing it with hot caustic solution and water or hot acid. So further, fermenters are made from stainless steel, but even stainless steel can corrode in the presence of high chloride concentration. One example is found in downstream processing. Oftentimes, saline solution is used, but if you heat up saline solution, it might lead to corrosion. And since the fermenters are very expensive, we cannot risk damaging our fermenters, and neither can a contract manufacturer. Also, you need to think about media preparation. It's a simple thing to pipette some milliliters into a shake flask, but it's quite another thing if you have a fermenter that only has one feed tank and you need to add 5 different fractions. And also you need to think about wastewater management. In the laboratory, it's no problem to just increase the concentration of trace element solution. But if you have to discard a cubic meter of broth, then it matters if you are in compliance with the wastewater ordinance or not. And also, you need to think about documentations. Your process has to be protocoled quite in detail to avoid problems later on in the scale-up. Now, going to downstream, oftentimes in our experience, much more attention is paid to to upstream processing rather than downstream processing. But the costs are basically the same in upstream and downstream. And in addition, if your downstream processing is ineffective, then you might have a high loss of products. And so it doesn't matter that your upstream process is perfectly optimized if you lose more than half of the product in the downstream processing. You need to think about scalability of your downstream process steps. One example is oftentimes in the lab, enzymes are recovered by heat precipitation, but this can be only done in a small scale. In larger scale vessels, you have a long time for heating up and for cooling down, so that overall your enzyme is cooked to death. Further, large-scale processes usually take much longer due to preparation times, transfer times, heat up, cool down times. So you have to think of places or time points in the process where you can stop the process and cool down and continue the next day. Otherwise, you are forced to work 24/7, and this usually costs much more money than just day shift operation. And also, I urge you to be pessimistic about your conversion rates and your yields. In large scale, you usually have lower yields than in small scale because of dead volumes and losses to processes not being run as efficiently and fast as in the lab. So I work for Fraunhofer CBP, which is an open scale-up platform. We basically focus on the use of the material use of renewable resources to produce intermediary products for chemical industry. And we have three fields of operation. First is pre-treatment, where we focus on extraction of valuable substances from a natural product. One example is we run wood fractionation plant of where we can fractionate about a ton of wood per week into lignin, cellulose, and hemicellulose. Also, we can extract products from oils and fats and so on. These intermediary feedstocks or pre-treated feedstocks can then be converted either biotechnologically by help of microbes and enzymes, or chemically by chemical reactions. And in the end, coming from a complex feedstock, you usually have a dirtier product after the transformation, so you need to have downstream processing. So we focus mainly on the scale up from 1 liter scale to 10,000 liter in fermentation. So together with our partners at Fraunhofer IGB in Stuttgart, we can provide the whole development chain for upstream processing from 1 liter fermenters to 10,000 liters. We are especially specialized in the use of lignocellulosic sugars, and we have at our disposal the most common downstream process equipment, and what we don't have, we rent. And we can produce sample material in kilogram to low ton scale, depending on the product. So I'd like to give you one process example, which was the production of itaconic acid in the project BioCat. Itaconic acid is a precursor of citric acid in the citric acid cycle. It is used in paints, especially often used as a coating material, and it might even be used for polymerization as a biopolymer. So the goal of the BioCAD project was to produce itaconic acid from low-value renewable feedstocks, like waste streams from sugar industry, in this case provided by Cargill. There was a development of the upstream and downstream process, and testing of the application of itaconic acid for different products. And our task was to demonstrate the upstream processing and downstream processing developed by our partners. So here is a bit on the upstream processing. So the fermentation was done with fungi of the Aspergillus family. And on the left, you see the product curves in different scales of bioreactor. We started at 100 liter and went eventually to 10 cubic meters. And where we are very proud of is that we reached similar curves in each scale. And we always reached about 110, more than 110 grams per liter in 7 days. The challenge really was morphology. On the right side, you see the morphology in different scales, and you see it is quite similar, but that was really the problem. If the morphology wasn't looking like that, we had almost no itaconic acid production. And in this project, so we had to pay attention, especially to agitation and aeration, so that the cell pellets get destroyed a little bit, but not too much, so that we retain those small pellets. And also important for the project was the preparation of the inoculum. And so the seed train must run perfectly to write morphology in the production scale. On the downstream part, the broth was filters. Some information for you. Filamentous fungi cannot be removed by separator. So while centrifugation might work in the lab scale, it will probably not work in crude with fast cool down. Itaconic acid was first captured. Again, cooled down and go to meter fermentation, so about 7 of. But it was enough for this. So that's something we have to improve on. So just a short notice, we are also participants in this transnational access. So we can help you to support your process development and scale up. We can give you preparatory data for your industrialization of the process, especially when it comes to mass balances and energy balances. And also, we can provide you with sample material. And with that, I thank you very much for your attention.